I guess we're gonna get started. Welcome everyone to the AstroAI Lunch Seminar. Today, it is my pleasure to introduce ChangHoon Hahn, who recently started a professorship at the University of Arizona and the Stewart Observatory after spending some time in Princeton as an associate researcher. Before that, he was a postdoc at Berkeley, and before then, he was at NYU doing his grad studies. He's interested in cosmology and how you use machine learning to exploit the big surveys for cosmology and for galaxy evolution. And today he is going to be telling us about Quasar spectral reconstruction and measuring the Lyman alpha forest. I presume they're using machine learning, but we'll see about it. The floor is yours. Thanks very much.
Yeah, I'll talk about machine learning. I feel like it'll be a pretty disappointed crowd if this is not using any machine learning. Thanks for the introduction. As Raphael mentioned, I typically work on cosmology and galaxy evolution, but this is a fun new project that I've just started sort of working on involving quasar spectra. So let me start with some introduction since this is also for myself since I know very little about quasars. But as you have light from a quasar traveling towards us here in the observer, as it encounters neutral hydrogen in the universe, you'll see that in the quasar spectrum down here that it leaves this line. Can't see my laser pointer, but you'll see these Lyman alpha absorption features that are imprinted on the spectrum. So this region is called the Lyman alpha forest. And cosmologists are particularly interested in this region for a couple of reasons. One is the fact that since you have these imprints as a function of redshift, you can use those to trace the matter clustering. So the neutral hydrogen in the universe, and then get the matter clustering. And the reason why Lyman alpha is especially interesting is you can use it to probe the redshifts of 2 to 5, which is a region that's particularly hard to probe with galaxy spectra alone. So people have used this to measure large-scale structure, large-scale clustering with the baryon acoustic oscillations. So you might be familiar with these two-point correlation function measurements from the DESI collaboration recently, where you can see here in this little bump, that's the BAO feature. So this is using the Lyman alpha forest on large scales in order to measure the BAO. Another reason why we're interested in the Lyman alpha is that it allows us to really probe clustering on the smallest scales. So because these are each probing the neutral hydrogen, that means that along the line of sight, you can actually probe clustering on scales that are only limited by the spectral resolution of your spectrograph. So what this allows you to do is really probe scales that are much smaller than what you can get with galaxy clustering. So just for reference, this is in Fourier space, K. The standard galaxy clustering analyses stop at around like 0.2. But you can see in this power spectrum measurement with different probes here, that the green, which corresponds to the Boss Lyman alpha measurements, it extends all the way out to K of around 3 or 4. So this is really the only way in galaxy clustering that we can really probe the smallest scale clustering. And this is particularly interesting for cosmologists because it allows us to measure things like the total neutrino mass. So I'm showing you here the residual effect of neutrino masses on the power spectrum. And you can see that as you have higher sum of neutrino masses, there's a larger suppression of the matter power spectrum on small scales. So if you look at this scale here, you can imagine we want to probe this region where the suppression is the largest and really continuously probe it in order to get that feature. So in particular for neutrino masses, Lyman alpha clustering on small scales is extremely important. If you're also interested in different models of dark matter, here's an example from the Ethos phenomenological framework, where each of these lines are different types of interacting dark matter models, where I'm showing you the transmission function here as a function of K, and you can see that on small scales of K to 10 or so, there's really big differences in how the interacting dark matter features apply. So we really need these small scale measurements in order to distinguish between these different models or measure neutrino masses. So that's another reason why we're really interested in the Lyman alpha forest. So because of the usefulness of the line alpha forest. Quasars are one of the main targets for the dark energy spectroscopic instrument, or DESI, which is currently observing in the Mail telescope, the 4-meter Mail telescope. You may have seen this already, but this is what the focal plane of DESI looks like with the robotic fiber positioners. There's 5,000 fiber positioners that allows us to observe 5,000 spectra simultaneously over the optical range with medium resolution. So this is just a slice through what DESI has observed in its first year and the different, I guess you can't really see this now. Well, the different targets are, tracers are labeled in different colors, and orange is the quasars. So you can see that we have quasars all the way going from redshift of 0.9 all the way to 3.5. That's observed by DESI. And so right now, DESI has finished its third year of observations, and it'll continue for 2 or so more years. Sorry. Yes. Maybe it's better if I stand there. And after the 5-year operations, it'll observe more than 3 million quasars altogether. By the way, feel free to ask questions if anyone has any questions, so we can keep it very interactive. So one of the challenges that we face when we're dealing with quasars, and whether it's for Lyman alpha forest measurements, is that we don't have access to the intrinsic true quasar spectra. So I'm showing you here, this is a mock quasar spectrum. So we only can observe the spectra after the attenuation. So here's what the true intrinsic quasar spectrum looks like. But the gray line, or the black is the Forster version of that, is the one that we actually observe. And so if we want to measure how much, yeah, go ahead.
How do you get this true spectrum?
This is for a synthetic spectrum.
Okay.
Where we know the true.
I see, okay.
Yeah. So we only observe the spectrum with the absorptions on top of it. And of course, if we want to know how much absorption is in the Lyman alpha forest or in the Lyman beta region here, we do need the true continuum in order to just measure how much depression there is. Now, the current state of the art is called PICA, and you can see this is just an example of it run on this particular spectrum. It actually forgoes trying to measure the intrinsic quasar spectrum, and it instead tries to estimate that expression over there, F bar times the continuum. So F bar there is the overall mean flux transmission. And moreover, they also assume this sort of form for how they fit the Lyman alpha continuum. So they assume that there's some universal function G in rest frame times this log linear function of lambda. So what happens in practice is that for each of the spectra, you're iteratively fitting for the A and B coefficients. So as you can imagine, that places a pretty restricted limit on what the quasar continuum can look like in terms of the slope and offset of these things. And I'll show you some examples of how this can fail quite significantly. So one of the reasons why this whole pipeline needs improvement is that if you just take the output of the state of the art right now, and then you were to measure the power spectrum, and then compare it to the true power spectrum you would know from the actual simulations, you get this huge discrepancy between the two. So because we're making these assumptions in how we get the continuum, we really get distorted Lyman alpha clustering. So this is one of the bottlenecks that we face, and why to this day, Lyman alpha clustering is still primarily focused on the BAO constraints that we get, and we don't really probe down to really, really small scales. So I learned about this problem, and I was wondering, could we actually get the continuum just from the observations? So without using simulations to calibrate it or train some neural network to predict the continuum, can we just take what we observed and actually reconstruct the quasar spectrum? And there's 2 reasons why I thought that was actually possible. One is that despite all of the attenuation that happens, there are definitely regions and spectral elements in the spectra that are unattenuated. And the other reason why I thought this was possible is that to 0th order, the foreground of absorption is uncorrelated with the quasar itself. So the position of the neutral hydrogen in the foreground of a quasar is not actually correlated with the intrinsic properties of the quasar itself, which means that it's for all intents and purposes, it's sort of a random absorption. So this led me to think, okay, well, I think we can probably use spectral autoencoders to do this. So I don't know if people are familiar with this, but it's been very successful at reconstructing galaxy spectra, and in particular,
Yeah, it's safer to assume people are not familiar.
oh yeah, I'm gonna go into there. So this is just showing you an example of it being applied to some of the galaxies in DESI. The black lines are the actual spectra we observe. The red is the reconstruction that we get from the spectral autoencoder, but I'll go into a little more detail about it right now. Yeah, of course.
So for the foregrounds not being correlated, are we sure that even within some like the same redshift range, that you don't have a positive correlation?
So there is, in terms of if you're within the halo of a quasar, then there's definitely a correlation.
And what about like in a 2 halo range? So like maybe on like 5 megaparsecs or so scale?
So there are definitely some features that are correlated. But in terms of the overall alignment output reports and ones that aren't in the same halo or 2 halo, then we can assume that they're correlated. I'll show some examples of when they are correlated, and then we can actually learn those features as well. So that's a great question. So here's a nice little schematic of how the spectral autoencoder works. So what goes into the autoencoder is the input spectrum and the mask and the weights that you have that you get from the observations. You put it into some encoder. The encoder, you can think of it as a neural network that compresses this input into a lower dimensional latent variable space, S over there. Then you have a decoder here that takes the latent variable as input and then outputs it to the spectral space. And so in a typical autoencoder, you would have the same dimensions in the input as you have outside of the decoder. And then you would look at the mean squared error of the two, and then you would train the neural network. And the motivation for autoencoders in general is that as you train both of these networks, you learn physically meaningful representations of the data here in low dimensional space. And so you can use this space to explore the data effectively, or also find nice reconstructions of it. So in terms of how Spender differs from a standard vanilla autoencoder is that we tailor some of the architectures specifically for galaxy spectra. So this is the encoder and then the overall architecture that we have. We have 3 different layers of convolutional neural networks. So this is the pickup spectral features. And then the really important part that we implement is this attention layer. So this is what happens is the convolutional neural network here outputs into 512 times 72 different spectral segments. And then we split that into 2, and then into H and K. And then we get A from one of those splits, and that A there serves as attention weights. So you can think of it as that weight there is determining whether and where the signal is. So to put it into sort of intuition for astronomers, that's the A there is what searches for like the DN 4000 break or like the H alpha. And we've actually shown that, for instance, one of those weights always corresponds to the strength of the H alpha flux, emission line flux. So that's the encoder. And then for the decoder, we have a simple multi-layer MLP, fully connected. And then another tailoring that we did for galaxy spectra is that instead of the decoder outputting to the same space as the input spectrum, it actually outputs to the rest frame spectrum. And then we explicitly impose this redshifting and resampling and the convolution in order to reconstruct the intrinsic spectra at the end. And then we compare this one to that one. So why would we want to do this? Well, we want to do it in rest frame because we want the latent variable to be redshift-invariant, meaning that we want this space to just correspond to the physical properties of galaxies and not a complex redshift-dependent space in order to maximize the interpretability of this space. The other thing is, if we train on galaxies over a relatively wide redshift range, if we reconstruct in rest frame, we can actually get a reconstruction that's wider than the input wavelength range that we have. So there's a number of advantages to doing that. Yeah.
sorry, friend, can you go back to the previous line?
Yeah.
Oh, I'm sorry.
Sorry, wrong button.
So what happens if you train this without the attention layer? So you mentioned that the attention sort of picks up the signals, right?
Yes.
You would have thought that maybe just by doing I guess these are 1D convolutional blocks.
Yeah.
So what is it that the convolutional blocks don't pick up that the attention layer is picking up? And would this be the equivalent to a vision transformer in a way if it was 2D, or is this a different architecture?
I mean, it is analogous to the transformer in kind. In terms of what the attention layer does is that because this is put in, input is an observed frame. This is basically getting some of the features in the spectral elements, and the attention layer is what allows us to sort of search through those features across wavelength to find them. So without this, it would be really hard to train a redshift-invariant latent space. Yeah.
And you say that your target is not the actually observed, but the rest frame one.
Yeah, so the reconstruction here, there's an intermediate step where we reconstruct to rest frame, and then we manually redshift it and then move it back into the intrinsic observed frame.
Okay, so that means you need to know that the redshift for all of your training data, right?
Yeah.
Oh, okay, so that's also an input.
Yeah, so that's an input here. Yeah,
Oh,
so
there-
redshift specified.
Okay.
So in DESI, we have redshift fitters that work quite well. And then we use it as an input. So we have also used Spender as a redshift fitter. But it doesn't work. I mean, it works pretty well. It just doesn't work super well.
Yeah.
It turns out that it's really hard to outperform brute force methods of finding redshifts for galaxies. Just because you can really do it in fine redshift bins, whereas this has we get the accuracy rate, but the precision of the redshifts are broader, so less precise.
And then finally, sorry, what is the mask here? What is that?
Oh, so in the observations, when we actually get the data, some of the bins are maxed out because of some issues with the reduction or whatnot. They also come with inverse variance weights for the data reduction. So this is like the output of the 1D pipeline of some spectrograph.
Exactly.
So, I'm still not sure how you get the rest frame data out there. So is that the attention layer sort of forcing you get the rest frame results there, or?
So we get the rest frame because of this explicit redshifting that we perform. So we have a fixed rest frame wavelength grid that the reconstruction outputs to, and then we redshift it, and then we compare it to the input.
But that's applied on the rest frame image first. So you get the rest frame image first.
Yeah, we get the rest frame spectra here.
How do you get that? That's my question.
So that's the output of the decoder.
Okay. But the redshift information is not there yet, right?
No, the redshift is an input. So we have separate redshift measurements that we have from the DESI spectroscopic pipeline. And so we feed in the redshift of the quasar and also the input.
Oh, so that goes into encoder.
Yeah.
Too. Oh, okay.
Yeah.
Do you diagram?
Well, so that redshift doesn't go explicitly into the encoder. It only comes in at this last step where we redshift it. So we've also tried architectures where instead of this redshift, we have the decoder predict both the redshift and the rest frame, and then we do the redshift manually and then compare it. But then the issue is that there is degeneracies between the reconstruction and the redshifting that causes some issues. Yeah.
So if I'm understanding this correctly, it's a choice that you're making to include the redshift after you sort of fit for the rest frame.
Yeah.
But the cost function is calculated on the final
In the observer.
question that you're getting.
Yeah.
So why not have the same step as the first, where you first convert it to its rest frame and then go through the process instead of, I mean, it's a conscious choice. I just want to understand the rationale.
Yeah, so the reason why we don't want to do that is that we want the rest frame to be as informative as possible, and also the latent variable space to be as interpretable as possible. So if we were to manually de-redshift it, then for instance, that really reduces the wavelength range where the reconstructions apply. Because now if you're manually de-redshifting a bunch of, now you're only reconstructing in that overlapping wavelength.
Oh, okay.
Yeah, so that's one reason. And then the other is, well, I guess the other reason is we wanted to see if we could do it. And it works quite well. So. Any other questions?
You mentioned interpretability. How do you perform? How is your latent variables? How are they interpretable?
So I'll get to that.
Okay.
Right away. So I talked about like the typical losses of autoencoders being the mean mean squared error between the input and the output of the decoder. Well, in this case, we have that MSE loss. We also have two additional terms for this. So the first term is the similarity loss. So what we do is, as part of the loss function, we actually have a loss that ensures that if we have two spectra with similar rest frame reconstructions, then they're also very similar in the latent variable space. So this further enforces this redshift invariance and interpretability into the latent variable space. There's also another loss that we add, which is consistency loss. And this is again to further reinforce the redshift invariance, where we, for each batch, what we do is we augment the data. So we manually redshift some of the spectra. And then we ensure that the ones that we manually redshift, they have the same latent variable, they occupy the same latent variable space as the original spectrum. Yeah.
Sorry. So the second term in your loss function that sort of makes sure that things that live close in the representation space also live close in the input space. Is that something you could have achieved with a variational approach to the autoencoder? You know, by sort of forcing the embedding space to be continuous in a way, like by using, you know, by not sampling directly into the latent space, but some probability to the parameters of a probability distribution. Or in other words, have you thought about extending this into a variational approach?
So this space is pretty continuous. We've done some downstream tasks where we fit a normalizing flow to that, and then we explore outliers through this. So the similarity loss here is not ensuring that galaxies of spectra similar here are in the same space there, but rather that two spectra with the same rest frame reconstructions also have similar latent variable spaces. Yeah, so that it's not just a matter of the smoothness, but really making sure that two spectra at very different redshifts that have similar reconstructions also occupy the same parts of latent variable space. Yeah.
How do you quantify the similarity of the space?
Sorry?
Like, how do you actually implement it? Like, do you have like a smooth function that you fit and then see how close they are, or is it just an L2 norm? Or
It's more or less an L2 norm. We take an L2 norm of the S and S space and the L2 norm of the reconstructed space, and then we have a sigmoid function that essentially ensures that this only really kicks in after this is sufficiently low. Okay, so here's some more examples of this applied to the spectra from the Sloan Digital Sky Survey. These are more broader examples. I think one of the things that I like to highlight with this is that because we're reconstructing on rest frame, you can see that for all of these spectra, we're actually reconstructing well beyond the limits of the actual input data. The other cool things are you can see regions where there's the gray bands or the shaded regions are the masked spectral elements, but we're able to reproduce reconstructions there as well that match some of the things that you observe. So one of the nice things about spectral autoencoders is that it does some level of super resolution. So depending on the redshift binning, wavelength binning that we impose for the rest frame spectral reconstructions, we can actually get super resolved spectra. So black here is the actual data that we input. This is red is with a reconstruction with a coarsely binned wavelength range over wavelength binning. But the blue here is when we apply a finer wavelength range. And you can see that we're actually able to resolve this O2 doublet, for example. And the reason why this is able to work is because of the fact that we're, let's say, for the same type of galaxy, we're observing them at different redshifts. So because the bitting of the wave spectral elements are slightly offset in those cases, you're actually getting more information than you have in otherwise. So this is one of the small advantages. We haven't actually found a great use case for this yet, but this is one of the things I would do. Yeah.
Would you say that the super resolution is actually working in this case? So naively, I would expect that if you choose like a wider window on the super resolution, it should converge with the red or the black curves. And it seems like in some of the cases it's over and undershooting.
What do you mean by it's over and undershooting?
The super resolved
Yeah.
spectra, if you take a smaller or a coarser window to match the under resolved or like the data
Yeah.
for the reconstruction. Like I see some of the people.
Well, so that's the red. That's like taking a coarser resolution reconstruction
Right.
in the red and then working back.
But if you.
Oh, you mean in terms of like, if we just took the blue and then we first resolved it,
Exactly.
then would it? Yeah, I mean, the normalization is not perfect, say. Yeah, so I see your point that if we were to just degrade the blue, we wouldn't necessarily get the red. But we are able to get more resolved features of the spectra, which is also quite important. Yeah, the normalization is because we normalize all of the data, and so a lot of that information is sort of wiped out.
So generally, when I do such fittings, I feel like when this happens, it means that I'm going beyond the number of parameters that actually is underlying the process. So for example, if you have a measurement and if you fit using higher than the Nyquist limit,
Yeah.
you're actually overfitting, which shows up in the super resolved space. So this reconstruction, is it using a very large number of latent space parameters?
Yeah.
Do you see if the super resolution actually converges better if you reduce the number of latent space parameters? Have you tried that?
No, I can't say we have, but that's a good point. We should talk more offline about that. Yeah, that's interesting. Yeah, no. Anyway, so I don't want to get too focused on super resolution because the talk that the application that I'll talk about actually doesn't use this at all. But what it does use is that because we impose the redshift invariance, we actually get physically represented meaningful latent space. So this is a UMAP projection of the latent variable space for, I believe this is Spectra from the Sloan Digital Sky Survey. It makes this kind of weird shape. And you can see here that there is some redshift dependence, but that also has to do with the fact that if you have a magnitude limited sample, you are getting distinct galaxy populations as you go. But you can see that overall in the lower redshifts that there's a good mixing of all of the different colors. Here's specific star formation rate, stellar mass, and the dust attenuation. And you can actually see there's sort of these gradients in the space, meaning as you move around in this latent space, you're really exploring different types of galaxies. So this is how we sort of, to 0th order, confirm that there is some physically interpretable meaning to the latent space. So if we were to just apply the Spender framework to the Quasar spectra, one of the issues we face is that because there's so much attenuation in the Lyman alpha forest, it'll overall suppress the reconstructions. And this is because of the mean squared error loss that we use. So what we actually have to do is combine Spender within this iterative framework that allows us to identify and mask some of the absorption regions and then iteratively reconstruct the intrinsic quasar. Oh yeah, I guess I already emphasized this, but one of the really nice advantages of this is that we're not training on simulations or calibrating on simulations. This is all data driven. This is just only using the data that we have. So that's a real advantage because otherwise, if you calibrate on simulations, you really rely on how accurate the simulations are before you can apply them to observations. So without going into even more details, let me just show you some nice GIFs of this working. So the red is the SpenderQ reconstructions, and the gray here is the observations. And you can see these shaded regions. So that's after each iteration, we identify the absorption regions. And so you can see the quasar reconstruction slowly moving up in amplitude. And at least by eye, after the third one, they're like, oh, okay, that gets in the true continuum. Here's another example with a little more interesting feature here. There's this massive broad absorption feature there. And so you can see after the first iteration, it automatically flags that as an absorption, masks that out, and then for the next iteration, it's able to just reconstruct spectra. Yeah.
Sorry, maybe this is dumb, but like, how do you know that it's right if you are just working off of the data? Like, I see like my eye, it like matches like the top, but like, how do you
But
know
that's
that
not-
everything is not like attenuated a little extra, right? Like,
I mean, that's not good enough. Like, just kind of squint and then go for it. No, of course, that's obviously not enough. So I showed you one synthetic spectral example. This is an example of the SpenderQ reconstruction, so we can actually see that it does remarkably well at reproducing the true spectrum. So in order to actually convince ourselves that this is working quite well, we applied this to 400,000 synthetic spectra that the DESI collaboration created in order to validate their entire Lyman alpha process. So this is an example from one of the papers down there that describes the mocks. So what they do is they take the continuum, they have these Gaussian log normal fields where they then position the quasars, and then they get these sight lines with all of this absorption that they put onto it. And then they get this noiseless spectra in the red. And then afterwards, they pipe it through the entire DESI forward model to get the noisy, realistic DESI spectra in the bottom. So they also go through the painstaking effort of putting in realistic astrophysical effects. So they have high column density systems, broad absorption lines, absorption features from other metal lines. So all of that is included to make the sort of the most realistic looking spectrum possible. So when we do this, here's 3 examples that I picked at high redshift so that you can actually see all of this region. Here's the Pika reconstruction, that's the state of the art. And here's the reconstruction from SpenderQ. So you can see it basically goes right through all of the blue lines. So it's able to do a really, really good job. So we ran this through all.
Sorry, so is the state of the art Pika approach only wrong at short wavelengths? Is that?
No, it actually just doesn't bother.
Okay.
Yeah, so that's
okay.
specifically for Lyman alpha forced reconstruction. So it's only over Lyman alpha and then below the Lyman beta region. And so here's the when we apply to all 400,000 and then look at the residuals and the distribution of this, you can see that we're able to really above Lyman alpha just nail the reconstruction completely. Here we get it right. I'll explain that in a second. And then in the Lyman beta, that's definitely the hardest part because you have absorption not from just Lyman beta, but Lyman alpha as well, and all the a bunch. So it's always a mess. And so this little feature here is because we apply SpenderQ to every single spectra that we have. Whereas in the standard practice, what you do is you first flag a whole bunch with broad absorption features, and then you remove that from the sample. But we didn't do that because we wanted to just see the performance over any type of spectra. As I just mentioned, the standard method excludes a whole bunch of spectra. So in the Lyman alpha region, they exclude 5% of all the spectra. In the Lyman beta region, they exclude 70% of the spectrum. But this is the performance for the spectrum where we don't have reconstructions using Pika. So you can see even here, it does pretty well. It's not perfect, but it definitely gives you some realistic reconstruction. So here's sort of highlighting why Pika is problematic. So this is again showing you the fractional residual. The blue is the reconstruction from SpenderQ. The orange is what you get from Pika. So you can see that in some cases it's doing fine. Pika is trying to estimate the black dotted line there. So for instance, the top right does okay. But then you can see in some of these other regions that it gets the slope completely wrong. And that's because, for example, there's this, you can see in the gray, which is the actual residual of the mock, of the spectra itself, that it's suppressed here so that it fits this extreme shape there. Over here, there's a suppression over here, so then it fits that slope. And so if you have these residuals, then you're misestimating the density fluctuations for each of these spectra. And so this will propagate and distort the Lyman alpha clustering that you get. So overall, this is a nice little demonstration that with SpenderQ, we're able to do individual quasar spectrum reconstruction quite well. So we've gone ahead and applied this to the public data set that was released by DESI, the early data release. And this is just 3 randomly chosen quasar spectra to showcase that. And we're reanalyzing the Lyman alpha clustering with this update. So you should expect that soon as well. So aside from the cosmology aspect of it, one of the things you can do when you have such reconstructions of the intrinsic quasar spectrum is do things like looking for IgM absorbers. So this is one spectra from the EDR. This is the reconstruction. And if you focus at these 2 little features here, you might be able to tell that they're in magnesium-2 absorbers at different redshifts. So what we can do is then we can go through all of the quasar spectra and systematically search for these features. So this is just a super busy plot that I don't know if it actually conveys information particularly well, but it's kind of cool. These are all the spectra where we identify absorbers, and we've sorted them based on the absorber redshift. The x-axis is the observed frame. And the reason why you would want to do this, the color is the transmission fraction, is that you can see these like lines that go through here. These all correspond to different absorbers. So we can assemble this catalog of IgM absorbers and then use that to study CGM or IgM. This is only a subset of them just because it takes a lot of time to make this figure. But we have already identified over 13,000 observers. The other thing you can do is just look at the actual distribution of the intrinsic quasar spectrum. So this is showing you the full distribution over the DESI EDR. That's like 200,000 spectra, I think, where we've normalized it at 1,700 angstroms. And you can see that there's this nice width of all the different shapes of the quasar. So one of the things that this highlights is that the assumption that we make with the Lyman alpha continuum just being some universal function times the log linear is clearly problematic here. The more interesting thing I think you can do is we can exploit the fact that we have meaningful latent variable compression embedded encodings of all of the spectra. So this is the UMAP projection of the latent variables in DESI. And one of the things that I want to highlight here is that all the colors are kind of mixed here. It represents redshift. So this is demonstrating that it's redshift-invariant. So what we can do is sort of move along this space and see how does the quasar spectrum change. So I don't know if you can see the color super well, but from that corner, moving around this little boomerang, I've plotted the different quasar spectra that's closest to those points. And so you can see that it actually, as you move through the space, it actually corresponds to the strength of the Lyman alpha emission. So you're getting intrinsically differently shaped quasars as you move through this space. Another thing you can do is look for like different parts of this latent variable space. So here, if you look at this little edge here, you're getting all of the blue, very blue quasars. So this is quasars in the early stages of evolution. You can look up there, and this is the dust obscured red quasars. So you can see they're very red shaped. And then, yeah.
Is there also a correlation with signal to noise in that representation space? Or
So I don't have the figure, but no, there is not a strong correlation between signal to noise, which is actually one of the things you'd want, right? Otherwise, if you have the same type of spectra but different signal to noise and they're in the different spaces, that means that the it's not as interpretable as you'd like it to be. So yeah, in this example here, I'm just taking a few of the spectra, but you can see they come in pretty different signal to noises. And so these are particularly interesting because this is before the AGM rolls out the dust. Here's ones with broad absorption lines. So you can see there's this, if you focus on the colored plots, then there's this massive absorption. This actually corresponds to the galaxies, the quasars where there's a halo and there's absorption happening there. So we actually, in these cases, sort of learn to ignore those. So that's also a useful way to sort of flag those objects because those are contaminants. The other thing you can do is then do some outlier detection. So these are just randomly selected quasar spectra where in the latent variable space, they are outliers. So most of these are pretty uninteresting, as you can see, because they're just redshift misestimates. So you can see that the emission lines don't line up with the black dash line. But there are some other objects that are pretty interesting, like for instance, the orange or the red, where you can see that there should be this lemon alpha, and the redshifts don't seem that wrong, but there's a massive absorption in there. So you can systematically go through all of the spectra and find some of these interesting anomalies or systematic failures in the data.
Is there a way you can tell from the list of anomalies which ones are misfitted redshifts versus actually interesting features? Or a different way to ask this question is how many spectra did you apply this to again?
200,000.
Okay, so I don't know, if you limit yourself to just 1% of the most anomalous objects, you still have a whole bunch of them.
Yes.
Is there a way you can assess which ones actually deserve follow-up?
So with just the latent variable space, I'm not sure. I haven't done this systematically yet. This is sort of hot off the press. But you can easily imagine a downstream check that you can do with the reconstructions in order to assess where the residuals are and then classify them quickly into different categories. Okay. So yeah, let me summarize here and just say that by using spectral autoencoders within this quasar reconstruction framework, we're able to get almost precision level reconstructions of quasar spectra. And I think a really interesting outcome of this is that you have an informative and physically interpretable latent variable space that you can use for different downstream tasks. And we are applying this to DESI EDR, so we'll have updated Lyman alpha clustering and also some interesting catalogs out of it, whether it's the reconstructed quasars, the latent variables, or the absorber catalogs. That'll be. And so the real next goal is to do unbiased Lyman alpha clustering of all of this using SpenderQ. Thank you.
I'm sure that was very relevant for at least a few of you guys here. Questions? Especially from those working on autoencoders. Comments?
Criticisms even.
Criticism? Yes.
I didn't catch if you explained that, but at the highest peak in some of your figures, there was a significant deviation of the measurement. If you go back like a few, I don't know exactly what slide it was, but keep going. You can probably see it here, but maybe like one more slide. So Spender had like a.
Here, this one.
Yeah, okay, if you look at the top right, or even the one below, all of them have
Oh yeah, that's actually
at the highest peak.
that's actually a bug that I need to fix. Because it's what we do is when we identify the absorbers, we do some rebinning in order to make the reconstructions a little smoother and then identify them. And I put kind of foolishly a difference. The binning is different on this side versus that side. So that just systematically always masks out that region so that there's like almost no spectra there, so it just goes to zero. But that's just a weird artifact there. Good question.
What method do you use to locate the outliers?
So in this figure that I showed, or these outliers, they were done in the most crude Jupyter notebook way of, I literally did, I just found the median of the latent variable space and I just identified all the objects that are farthest away. because I was like, quickly hacking this together for this talk. But in principle, you should do something better than that, which is I would probably fit the distribution of the latent variable space using a normalizing flow or some other neural density estimator, and then look at the probability that's actually predicted by that density estimate, and then impose some threshold on that, and then identify the outliers that way. So we did that for the some of the DESI galaxies, the galaxy spectra, and we were able to find a bunch of interesting objects and contaminants that way. Yeah, so that's much more systematic.
But you show some trend in the latent space with like physical variables like salt emission too.
Yes.
So, varies in the latent space. Is that a way to like quantify that correlation in the latent space?
You're talking about this figure, right?
Yes, this shows like some little qualitative picture. Is that a good way to quantify this correlation between the physical and parameters?
So I think this is more of a qualitative assessment of this, because this is a 2D projection of, in this case, I think it's a 10-dimensional latent space. So that just tells us, I guess, for my brain, whether there is some dependence in the latent space. In practice, though, if you wanted to really quantify how much information about all of these parameters the latent variable space has, what you can do is use the latent variable as a compression of the spectra, and then actually try to predict these parameters. And so in the case, let's say that the autoencoder is super optimal, extracts all the physically relevant features from the spectra, then whether you fit the full spectra versus the latent variables, you should get the same constraints on these parameters. But if it's lossy, then you'll find that it's broader with these. The prediction will be broader than you would get it with the full spectrum. In this case, for these spectra in particular, it is lossy. So it doesn't retain all of the physical information.
I like the fact that these actually look like brains, that you might have achieved artificial intelligence,
Yeah.
actually. Anyway, that's the stupid joke with which the talk seems to be over. So I forgot to mention that you're visiting for a semester, right? I think you might disappear at some point, I understand, but you're sitting in P3.
321.
321, so if people want to show up at his office and talk about autoencoders or galaxies, please do so. Thank you very much. Let's thank him again. See you all next week.